Great. Okay, so hello everyone. So my name is Tyler Chang. I'm currently a postdoc at Argonne National Laboratory, and I work in the mathematics and computer science division. We actually, in my particular group, we mainly write numerical software for, I think, large-scale simulations and things like that. We maintain a lot of libraries for doing these kinds of things at scale on supercomputers and these types of environments, specifically for like scientific domain type problems and stuff like that. But we have a lot of very general purpose libraries. I don't know if you guys have heard of like PETSC and FlashX and things like that. A lot of these products are actually maintained by Argonne staff. So I don't know. I thought I'd maybe start by just giving that background on what we're up to here. I see, yeah, it looks like, maybe not such a huge group. So I'm gonna talk for maybe about 10, 15 minutes and then try to get into a 30-ish minute tutorial. But if, as we're going through this, if you have questions, please feel free to just unmute yourself and interrupt me, and I'll try to clarify whatever I can. Okay, so yeah, so I guess first of all, hello everyone. Hi everyone, nice to meet you all, and thanks Joseph for inviting me to talk here. So myself in particular, over the course of the last 2 years, I've been developing a software package for multi-objective optimization of simulation-based problems. So these are problems that sort of depend on the output of some expensive simulation, or in some cases, like a real-world experiment where we have to go to the chemistry lab or something and do an experiment to see what will happen. And we want to optimize the outcome of these processes. And we want to do so with respect to more than one performance criteria. So that's where the multi-objective aspect comes in. And so what I'm going to be talking about today is just a very general framework. And I want to emphasize that there's multiple ways of solving these types of problems, but this is like my favorite flavor of how to do it. So that's what I'm going to talk about today. And I think it's, I think with respect to modern trends in machine learning, and also with sort of bringing in some domain knowledge, I think this is the best way to kind of take advantage of some of these technologies and knowledges. So, so yeah. So I'm going to give a 15-minute overview, and then we'll jump into a quick tutorial on how to code up some of this stuff in the library that I maintain. So, what's going on here? Okay. So to start out, I don't know what everyone's background is, so hopefully this isn't too boring, but I want to start by just doing a very brief overview of maybe some basic calculus type stuff. In particular, just kind of classical optimization algorithms. So here's just an example that I made up of an optimization problem one might want to solve. Say we have some computer chip on a circuit board, and now we want to place another one. And I've made this a one-dimensional example, so we can only place it along this x-axis line. And we want to get it as close to this chip as the existing chip as possible, so that we minimize the amount of wire we have to lay, and maybe also minimize like the communication delay or something like that. So we can formulate this mathematically. We have a function, which is the distance function. It's a function of the position x on this axis. And it tells us, for this x coordinate, how far are we from the chip? And in particular, sorry, on my screen, it's cutting off here, but yeah, we have, I'm gonna be minimizing the squared distance just because it makes the optimization problem easier to solve or look nicer in this example, but it's the same thing. Okay, so I want to minimize this squared distance. Suppose this chip is at like coordinate x equals 0, then it might, you would get a nice equation that looks something like this. And I think we probably already know the answer to this problem, but let's pretend we didn't and we wanted to solve it using some optimization procedure. How would you do that? We can put on our calculus hats and remember how to calculate some derivatives. So if I just pick some initial place that I might want to put the chip, say I start at this point over here. If I calculate the derivative of f of x at this point, the derivative tells me like the uphill slope. So the derivative will actually point in this direction, and then the negative derivative tells me the downward direction if I want to make my f function get a little bit smaller. In other words, get closer to the chip, right? And so one very simple thing you can do, it's called gradient descent, and it's kind of the basis for almost all of optimization, is you just iteratively, you pick a location, you look at the negative gradient, and you take a step in that direction, and then you get a new point, you calculate the derivative at that point and keep taking these negative gradient steps until you get to the bottom of your cost function. And then you say, okay, when the gradient gets very small, you say, I'm close to 0, so I'm pretty much done here, right? And of course, this is a 1D example, but in multiple dimensions, you have a gradient instead of a one-dimensional derivative, and then the gradient is truly like a multi-dimensional direction, not just a left-right arrow. So hopefully that feels warm and fuzzy to people who have, those of you who have taken some calculus courses before. And yeah, so, and I want to emphasize, this is, if you have derivatives, you should do something at least similar in principle to this. And most machine learning models and stuff like this, I mean, this is like the foundation for almost all of machine learning. It's very much used. But in the case where our cost function is the output of some expensive simulation, which is the types of problems that I work on, it's a bit harder because well, first of all, we don't want to evaluate if our simulation takes like 10 minutes or an hour or something to run, we don't want to evaluate it too many times. So that's one concern. But additionally, it's very hard to take the derivative of some complex simulation output. I will say, I say that with an asterisk, it's actually possible. There's lots of people who do research in algorithmic differentiation, which is like, how can you propagate derivatives back through a complex process like this? But it's very difficult to do and expensive, and it's not always possible. So what can we do in these situations? So this is now, we're getting into the realm of simulation optimization, which is what I'm interested in. And so for these problems, we say, okay, I can't get derivatives, but I can, with great expense, just calculate the function's value. I can run the simulation, I can see what the output is. I can just query the article. Okay, so what could you do in this situation? Well, perhaps the simplest thing you could do to mimic gradient descent is just, instead of taking one evaluation, I'll take one evaluation and then another like nearby and do like a finite difference approximation. So just like fit a line between these 2 points and say, okay, the slope of that line is going to be very close to my derivative, so I can just follow that downhill, right? And we would call this a linear model or a linear surrogate in this example. But I mean, and this is what people, this is one of the common algorithms, and it's what people did for a long time. But especially in recent years, people have kind of thought, well, you know, why stop there? If we have a larger data set, which especially as you run your simulation many times, you start to collect a large data set of outputs, you can do something much more complicated. And so you can have a nonlinear surrogate. And I don't know if how visible this picture is, but this line is curved, right? It's not just a line anymore. And this could be the result of fitting some machine learning process, some statistical method or something. And it could involve more than 2 data points. It could involve your whole data set. Some interesting examples of this maybe that might be relevant to other things on the agenda for this, for the next couple of weeks for you guys. I've seen some people doing this, like where the surrogate is like a physics-informed neural network, for example. So you can do some really creative things that are really specific to your problem, right? You don't just have to do like a black box algorithm in a sense. So hopefully that makes sense. So that is kind of, and then when you fit this model, hopefully it's a differentiable model, right? And then you do gradient descent on this computationally cheaper model that has an easier equation to analyze. And when you've minimized that model, then you say, okay, I'll take an evaluation there, and that's my next iterate point. And I update all my models and solve the problem again until I've converged. So hopefully that overview makes sense to most of you. I'm going to pivot into some multi-objective stuff now, but if you have any questions about that, now would be a good time. Okay, so if not, let's keep going then. Okay, so that's sort of, I would say, the first like real world consideration, right? We've changed just gradient descent because we can't always get derivatives in the real world. The second change I want to make is that sometimes it is hard to just, sorry, I have something in the chat. Okay, great. So sometimes it is hard to just have like one objective, right? Just say there's just one thing I want to minimize. Sometimes in the real world, you have many things that you care about, right? And in this presentation, by the way, I'm always assuming that you want to minimize things. If you, by chance, you wanted to maximize something instead, you can always just minimize its negative value. That's the trick we use in optimization. And that way we can just assume you want to minimize everything. It makes life easier. So say there's 2 things I want to minimize. And I think now if this is like my chip placement function, say I also want to minimize the distance to another chip that's placed somewhere else, right? So I now have 2 cost functions that I want to minimize. I can put it really close to the first chip, and then I'll just be at the bottom of my 1 cost function, but I'll be really far away from the other, right? And I could also put it over here and have it right at the bottom of this cost function, but then it's really bad for this one. So it's no longer clear what is the optimal place to put something, to place the component. And in fact, I could place it really like anywhere along the line between these 2 points, and I'll get some kind of trade-off between how good it is with respect to these 2 criteria. There's also some stupid things I could do, like I could put it over here and then it's just going to be bad for everything. But there's not one clear answer in this case. And to understand this, we have something called a dominance relation, which basically says if I have some points in my objective space, so this is my F1 value and F2 value, these are some results I got from running my simulation or whatnot. Some of these points I can do better in every way, right? So if I look at this point here, for example, I could make this better in every way by choosing this one instead. This is lower in both F1 score and F2 score than this point. And so we say that that dominates this one. And so another way of thinking about that, I'm stealing this joke a little bit from some other famous optimization people, Stephen Boyd, who's a famous optimization guy, but I like the way he explains it. Another way of thinking about that is, this is a stupid thing. You would never build something like this because I can build something else that's better in every way, right? So the solution to the multi-objective optimization problem is not a single point. It's just everything that's not stupid, right? So in this example, these 3 points, I can't do better in every way than any one of them. And so as the optimization guy, it's none of my business which of these is actually the best, because that depends on what the engineer or the domain expert thinks when they've solved the problem and they look at this trade-off curve. So my goal is just to give you all of the not stupid points so that you can decide what you actually want to build. And so that's really the goal here. And the way we do that is we have something called a scalarization function, which basically collapses. You don't have to worry too much about this math here, but this is the basic idea. We have a function which takes our multiple objectives and collapses them into a single objective. And when I solve one scalarization, if this is my true trade-off curve, when I minimize one scalarization with a single objective optimizer, I'll get 1 point on my trade-off curve. Or we call this the Pareto front. And what I'll do is I will have a family of scalarizations that I can kind of jump between them. And by solving many of these, I'll get many points on my trade-off curve. Each time I solve one, hopefully I get a different point. And then hopefully if I do this enough times, I get a lot of points that sort of discretely approximate my trade-off curve. And so the goal is really to get enough of these so that you have a good understanding of what that trade-off curve looks like. And the policy for scattering these across the trade-off curve is called an acquisition function, is what we call it. And so you'll see that term come up when we get into the tutorial. The acquisition function is basically like it's a function, it's a family of functions that lets me scatter solutions across my trade-off curve, hopefully somewhat uniformly. And I think the example we'll use in the tutorial is, for example, just uniformly spaced weights of the two objectives we're going to look at, right? So I can see like 60% one, 40% the other, 50-50, 40-60, and so on to get a bunch of points on this trade-off curve. Okay. So that is the main idea here. And yeah, so I want to point out that there are actually several algorithms for doing things like this. Sorry, I have a question here. I have how to decide how many points to be considered. I guess you're asking about how many solution points do we want at the end? I think that's what this question is asking. So generally with these types of problems, the restriction is on like the budget of how many simulations you can run. So, right, maybe.
Hey, Tyler, sorry to interrupt. So it is the previous slide. So the slide in which you showed some points, plotted some points, and chose the minimum. Yeah, that's it.
Like how many points to evaluate?
Absolutely.
Yeah, typically it's a budget given to us by based on the cost of the simulation, right? So, for example, I worked on a problem recently where the cost of running our simulation on several nodes of the supercomputer was like 10 minutes it took about to run on maybe several nodes. That's to evaluate the simulation one time. And then, we wanted to finish our runs in 2 weeks or something. And so we calculated, okay, for that much time, we can maybe do 1,000 or 2,000 simulation evaluations, right? And then so we give it a budget like that. Typically, that's a function of how much time you have, how much resources you want to spend, and how expensive your simulation is to run. So that would be my answer to that question, and I think we'll see that in a couple slides in the tutorial. Okay. Sorry, I see in the chat there's some audio problems, but I think that person is having the issue on their end. So I'm gonna keep going, but I guess let me know if other people are experiencing similar issues. Okay, so we're looking at this problem, right? And as I said, this black box process could come from some numerical simulations or some real world experiments, something expensive. Doesn't have to be just a simulation. There are many packages out there actually for solving this type of problem using surrogate modeling. It's not like ParMOO is the first one that's ever been created. So I wanted to take just a second to say why did I bother to create yet another one? So some of the existing ones out there that are very good, and I don't mean to slight any of them because I think they're very good packages. There's a package called ParMOO, which is more of a modeling language for setting up your simulation and then a model that you want to use on it. There's another one called Dakota. Both of these are maintained out of Sandia, which is a sister laboratory to us. There is, in the engineering domain, there are some specific ones. I think PySMT is a good one that I've seen some good things from. OpenMDO is another good one. So there's other things for sort of doing this sort of surrogate modeling based optimization process. I think one of our secrets that makes us a little unique is we try to look at this intermediate space. So a lot of the time, your simulation is not actually the thing that you're optimizing. You have some objectives that you have some simulation output, which is maybe I don't know, some flow field or something like that. And then based on that output, you have some cheaper to calculate objectives that you stack on top of that output, right? And that's how you actually calculate the quantity that you're trying to minimize or maximize. There's actually additional structure encoded in these objectives that you can exploit. Additionally, a lot of the existing, not all, but a lot of the existing ones don't really support a generic surrogate model. Maybe they have some library of built-in surrogates that you can use. And so we try to empower people to somewhat easily bring in their own customized surrogate. For example, if you had some physics-informed neural network or something like that that's really specific to your problem, and you want to bring that in and use it to directly model the simulation outputs and then stack your objective on top of that. So you will see that distinction when we get into the tutorial in just a second here. Just to break down the key components, when you're running something like this, you can't fit a surrogate without data. So the very first thing you do is you generate a design of experiments for your simulation, right? Just some points that you want, some inputs to your simulation that you want to evaluate so that you can have a good data set to start fitting some models to. Then you needed to pick the surrogate model for modeling each of your simulations outputs. Then you need to pick some family of acquisition functions. And you need to choose a single objective solver for solving those scalarized problems. And so we allow you to use our library of pre-existing techniques for each of these or import your own custom technique. And then we do the rest of all the messy stuff of sticking that together with your simulation evaluations and hiding all the complexity of making the algorithm run. And if this will work for me, let me see. I had a little animation here. Yeah. So here, we're generating, we have two objectives, and we're generating some design of experiments that we want to evaluate. We send these off to the simulation or the experiment chamber, or the wet lab, whatever, to evaluate them and get some data points. And then once they're all evaluated, we fit some surrogate model to those data points to approximate what's going on. Then we optimize on these surrogate models with respect to some acquisitions. And this gives us some targets that we think are good points to evaluate in the next iteration. We send those off to the lab, evaluate, or to the simulation software, evaluate those and update our models. And we just kind of iterate like this until the budget is exhausted. So hopefully that gives you a good idea of what's going on here and how things are going to work. So with that, I think, where's my slides? I think it's time to jump into a tutorial. So before we do that, does anyone have any last questions just about the theory here, or should we get started?
Yes, I do. Can you guys hear me?
Yes.
Yeah, so if you go back to the slide that you were presenting, so how do you choose those design variables, right? Like, I think it was in the it was in the web that you showed.
Yeah, I mean, like here, right, you have some input variables that you can tune over.
Exactly. How do you choose where to simulate that objective function, right? Like, how do you decide that?
So, yeah. Okay, so what you said is how to choose the design variables. For me, that's a little bit outside of my domain, right? Mm-hmm. Because I'm not really a domain expert here. So someone is going to come to me with their problem, right? And so, they know what the inputs to the simulation are that you could alter to try to come up with a good design. Is that what you're asking about?
Yeah, that's what I was asking.
So that's really something that the domain expert has to come to us with, right? Like, these are the parameters that we're trying to figure out, maybe in the example of CFD, for example, one parameter might be the angle of attack of a wing. And so it's what angle should we set this wing at so that it will, so that it will produce maximum lift. Does that make sense?
That makes sense. Okay. Right.
Yeah.
Thank you.
So that maybe that's an example. I don't know.
No, thank you.
Okay, great.
Hi, Taylor.
Yes.
I have one doubt. Yeah. So you mentioned based on the budget of the process, we'll consider the points. So can I know how do we incorporate the physics of the problem? Is the physics of the problem considered while choosing the data points, or is it randomly we'll choose the points based on the budget?
So I think usually I said there's two steps. First, we just do some design of experiments. Usually in that design of experiments step, you just want some space filling design. So you have some good data set. And even if some of them are bad, it's actually good for the machine learning models usually to see some bad examples too, so that it also can tell what not to do. So in my experience, that design of experiment step, it's not necessary to necessarily always encode some of the physics structure into that. The place where you can really benefit from bringing in some physics structure is in choosing the acquisition function. So you may know, for example, that not everything that's Pareto optimal is good for the physics, right? And you can often encode that in a customized acquisition function, if that makes sense. Another place is when you're defining the simulation surrogates. So for example, if you were to use a physics-informed neural network, then it's the surrogate model can't just generate any old model, right? It has to generate a model that obeys the physics of your problem. But I don't have anything built in for these specific applications because again, like that's outside of my domain. So more, I'm trying to provide a framework with some basic building blocks where then you could pull in something like that and use it as your model.
Thank you.
Yeah, and yeah, so Joseph said you guys are going to talk about those next week. I saw it on the schedule. That's why I keep bringing it up as an example. Okay. So let me jump into a tutorial here, and oh gosh, where am I? I think this is what I want. No. This one. Okay. So let me jump. Okay. So can you guys see my screen here? So I am going to jump into a blank Conda environment, just to show you what it would look like to install this on a new system. You don't necessarily have to do that. I don't think there's I don't have a ton of non-standard dependencies, so I don't think there should be a huge risk of like environment conflicts or anything, but it's always perhaps a good idea to do something like this when you're installing new packages in Python, because but if you don't understand Conda environments and stuff, maybe just don't worry about this step. So I already had created a Conda environment called ParMOO demo. So I'm just going to activate it. Okay, so I'm in this blank environment. So there's several ways to get ParMOO. I think the easiest, it's on CondaForge channel, so you can also get it off CondaForge. I just added it to CondaForge like a week ago, so it's not in the docs yet, but it's called ParMOO and it's on the CondaForge channel. The other way to get it, which I think is probably easier, is to pip install. So I'm going to pip install ParMOO. That's the command. I always use this Python 3-m thing just to make sure it doesn't. I've had some problems with it conflicting with my pip doesn't agree with my Python version for some reason. I can't get it to work. I can't get it to fix it. But anyway, when you do this, it should go to the PyPI repo and download all the dependencies and stuff. So, so if you don't have to necessarily follow along with this because I sent Joseph like the basically like the solution key of everything I'm going to type up. So if you want to just like watch and then kind of go study that script and try to play around with modifying it a bit on your own time afterwards, you can feel free to do that. But if you want to follow along, then the first step is to pip install ParMOO. And the other one that we might use, which is not part of ParMOO, is matplotlib. So, and that's not part of ParMOO. I'm just using that for some, to show you some of the demos here. Okay. Now, in that zip file, I also had a template for the tutorial. So if we look at that, it looks something like this. And this is just defining the problem that I want to solve, so that I don't have to rewrite all that code from scratch here. And I'm just going to show you, we're just going to walk through this file, and then I'm actually going to run it in the REPL so that we can do this in interactive mode. But I just want to walk through the lines of this file with you first. So first of all, I'm importing NumPy, and I'm creating this blank data set. So I have these 3 data points that I am, these 3 data points that I want to fit. They're just points in the plane. And what we're going to try to do here, I scattered those data points just so you can see what they look like. But what we're trying to do here is I've I don't know how many of you are familiar with inverse problems, but I made up what's called an inverse problem. So we have some function f of x, and we want to fit it so that it approximates our data set. And this function has the form of a polynomial. So we're trying to find the coefficients of the polynomial, a, b, and c, so that ax squared plus bx plus c matches our 3 data points. We have right, 3 x values and 3 y values. So this is, for those of you who remember, you have a polynomial of degree 2 it's possible to find coefficients so that it exactly matches these 3 data points. But one of the things that sometimes you want to do when you're solving these inverse problems is keep your coefficients small in some sense. And what this does is if you have a problem where there's some noise in it, it prevents overfitting. So this is going to be our second objective, is to keep this a squared plus b squared plus c squared small. We call that a regularization term. Yes, yeah, sorry. I'm one of those people. I work in Vim. So it's not I was trying to actually make a Python notebook and like a Jupyter notebook last night, but I'm a Vim guy, and I was trying to learn some new stuff, and it was like, this is not going to happen in time. So I'm going this route. Sorry about that, guys. You can use whatever your favorite IDE is, or in a second, I'm going to just run this in the REPL. So I've defined a function which basically evaluates my polynomial. So I give a, b, and c and the point x that I want to evaluate, and then it will just return the value of my polynomial. I also made a little nifty function for plotting a polynomial based on the values of a, b, and c. Okay. And then I have defined, in our example, the simulation, and this is not a real simulation because it just has to evaluate this polynomial. But I didn't want to run a real simulation here because we'll be here for hours. So in this example, I'm just, you can imagine, right, that instead of a polynomial model, you could have some simulation that's based on 3 parameters as well, right? And so the output of my simulation in this case is the error between the polynomial that I'm fitting and the data points. Okay, and you'll see why I defined this way in a second. It has to do with, you'll see when I define the problem. But let me just run this script real quick so that my plots will pop up. I don't know why it's taking a while. Okay, so these are the 3 points that I created for my data set. And then I just plugged in some random coefficients to a polynomial, and this is what it looks like. Okay. And obviously I can change those values of a, b, and c, and I'll get different polynomials, and I want to find one that's going to closely trace to these data points, but maybe not exactly match them. Keep this polynomial kind of not too curvy in a sense, because we would think of that as maybe a symptom of overfitting. Okay. So now I'm going to start up my Python REPL. And so if you have your favorite IDE, right, that has like a Python command prompt, this is basically that, but I'm just running it in the terminal. I'm going to make it a bit larger. Hopefully that's maybe a little easier to see. Okay, so the first thing, let me just import my template. So this, when you import a file, it just runs all the commands in that file so that all my functions and stuff will be defined and I don't have to redefine them here. It's going to run my plots again. Okay. All right, so now just this basically is the same as typing all the code in that file into here, so I have those defined. And so now here is how I would go about solving this problem in ParMOO. The first thing that I need to do is import like the basic objects in ParMOO. So ParMOO is an object-oriented language. So we're going to define a MOOP object. MOOP stands for multi-objective optimization problem. So I have a MOOP object, and then I add properties to that object, things like design variables, simulations, objectives, and surrogate models, acquisition functions, and things I want to use to solve the problem. So I'm going to go ahead and from ParMOO, I'm going to import my MOOP object. And one of the first things I need is the optimizer, the single objective optimizer that I want to use to solve all of my scalarized problems. So the particular one that I'm going to use is called local GPS. So when you get more advanced, I would recommend using something gradient based, but this is a gradient free optimizer. And it just makes it easier for the tutorial because I don't have to define derivatives of my objectives and things like that. So we'll get through this a little easier. But if you go to our documentation online, there's tutorials on how to do the derivative stuff. It's just a few extra steps, but we can avoid that by just using the derivative free optimizer. Okay. And now to create the MOOP, I'm just going to name this my MOOP, and it's going to be a MOOP object, and I have to provide it with at least one argument, which is the optimizer I want to use. And so that's what I'm doing here. Okay. All right, we have something in the chat. Okay, yeah, Yosef has dropped the documentation. I'll come back to my slides, and I have all our resources on one slide, but I was going to run through the demo first. Okay, so now I'm going to add 3 design variables to this problem, and the syntax for that is mymoop.addDesign. And the 3 variables I want to add are my A, B, and C. So I'm going to give each of them a name. And if you remember from that template slide, like I was referencing them from like a dictionary by their name. So like I was like taking like input.a and stuff like that. This is why I had to do it like that. It's because I've given them these names here. And I also have to specify lower and upper bounds for the range of values these variables could take. So I'm just going to tell it here that the lower bound on my A variable, so this is like the A coefficient in ax squared plus bx plus c. It has a lower bound of 10, and we'll say it has an upper bound of, a lower bound of -10, and we'll give it an upper bound of 10. Sorry, I need these. This input should be in a dictionary, sorry. Okay. So now I have one design variable for my problem named A. And I'm going to do the same thing and add another variable named B and another variable named C with the same bounds, right? And so these are my A, B, and C coefficients. And I'm going to tune these, like I said, to find the best polynomial for fitting my data. So now I need to add my simulation. When I define my simulation, I also have to define what technique I want to use for generating my initial design of experiments. So the initial sample for getting some data, and what surrogate I want to use to model the simulation. So I'm going to import a couple extra tools for doing that right here. So the first one I'm going to do is from ParMOO.searches. I'm going to import this Latin hypercube design. This is pretty standard. It's like the standard technique people use for doing these design of experiments. I think as of now, I think it's the only option available in our searches library. It's sort of like a random sample, like just generating random points, but it has slightly better statistical properties especially when you have a lot of design variables. It's taking a second here. Okay. I think because I did a fresh install, it has to like build some stuff on first import. So some of these take a second to run. And then I also need to import my surrogate model. And so I'm going to go to our ParMOO.surrogates library, and I'm going to import a Gaussian RBF surrogate. So this is just a classical statistics method. It's basically, it's a Gaussian process, if you're familiar with that, but it's a statistical model for fitting a response surface to your data points. And, you know, this could be something, like I said, that you could replace if you have some structure exploiting machine learning model or something for your problem, then this would be the thing you would replace it with. But if you don't have anything like that, or even if you did, if you just wanted to like solve some baseline problem to see how things work with just from a baseline, this would be like kind of the standard first step to go to. Okay. And okay, so now I'm ready to add my simulation to the problem. And remember, I had already defined the simulation function in that template that I showed you, the template that we walked through earlier. So I'm just going to add that. It's the error between it outputs 3 errors. It's a vector valued simulation. The output is 3 errors, the error and fit for each of the 3 data points. So I'm just going to add that function as the simulation for this move object. You can have more than one simulation if you want to, but in this case, we're just going to have the one. I can name it whatever I want. I'll name it my simulation function. You could come up with a more creative name based on your problem. I have to tell it that this simulation has 3 outputs. So that's what this m equals 3 is going to tell it. I need to tell it what the simulation function I'm running, what simulation function to run here. And so we're going to have it run the mySim function, which was defined in the template. And then, okay, let me go to a new line here. I have to tell it what search technique to use, and I'm going to use that Latin hypercube search that I just imported from my libraries. What surrogate? I'm going to use this Gaussian RBF process, and we can tell it some hyperparameters for each of these models here, and these basically get passed to the hyperparameter field in the definition of the Gaussian RPF and Latin hypercube. That's perhaps opaque to you from here, but this makes it easier if you are defining your own methods, then you'll need to pass. This is how you would accept hyperparameters if you were using like a custom method. And for here, I'm going to tell it, I'm going to give it one hyperparameter, and it's going to be the search budget. This is telling it for that initial search, I want a Latin hypercube of 50 points. So like before I even start optimizing, just do 50 experiments to get some initial data. No, my sim is not defined. Why not? Sorry, let me open a new window here, see why not. Where's my sim? Maybe it's going to be, I think maybe it's template.mysim since I imported from the template. Yeah, that worked. Okay, sorry. So you have to do this template dot notation because we imported from the file named template. Hopefully that makes sense. Okay. All right, so I have a problem that has 3 design variables and a simulation that accepts those design variables as input. Here we can, sorry, where did this go? Since I had it up, we can look at it again here. It's here. So here's my, here's the definition of my simulation, right? It evaluates each, it has 3 outputs, evaluates the polynomial at each data point, and it's like outputting the error, like the misfit error, or the difference between what it, like what the polynomial outputs and what the data point actually was. Okay, now I need to tell it what are the objectives, right? So what am I actually trying to minimize here? So to do that, I'm going to use the add objective syntax. And so the first thing I want to minimize, we'll call it the chi-squared error. So this is just going to be the sum of squared errors. Right, so the sum of the squares from all of those errors, right? I would like to minimize the sum of squared errors. That will, if I exactly minimize that, that will produce the polynomial that actually exactly matches those, that like exactly hits all 3 of those data points, right? So that's the first thing I want to do. And the equation for this, so I have to give it an objective function. And typically you should define an objective function. Do not use lambda functions because it will mess up running in parallel. So lambda functions don't play nice with our parallel solvers. But I'm going to run everything serially here. So I'm going to cheat and use a lambda function to make this go faster. So the objective function has to take 2 inputs. It's the design variables and the simulation outputs. So that's what these 2 values are. Okay. And I'm telling it that for each of my simulation outputs, so for each S, I want to calculate the, I want to minimize the chi-squared error, right? So I'm looking at the, let me actually do this on a new line, sorry. This is going to run off the page. So my objective function is going to be to minimize the squared norm of my simulation function. Does that make sense? So I have my simulation function. It's going to have those 3 outputs. I want to minimize the squared norm is the sum of squares for each of those output fields. And so that is going to be my first objective that I'm adding to the problem. Oh, NumPy is not defined because I imported it through that template. So I need to do this first. And then now I can add the objective. What does it mean? S is not defined. Oh, sorry. I didn't put the lambda in here when I redefined it. Okay, this should be correct now, right? There we go. And I have a question in the chat. So yeah, sorry about that. I dropped the lambda when I split onto lines. Okay, and now I'm going to add my regularization penalty. So this is the other thing that I want to minimize. We'll call it the L2 regularization. And what I want to minimize here is not my simulation outputs, but still I want to minimize the this is going to depend only on my X input, not the simulation outputs, this objective, right? So I have the A field of my X plus the B field. These A's and B's come from, remember I named these A and B when I added them. Squared plus XC squared. So this is my regularization penalty. I'm telling it that I want to also minimize the sum of these squares. Okay. And now I have defined the problem and I'm almost ready to solve. There's just one ingredient left, and that is those acquisition functions. I need to tell it how to scalarize these two objectives. And so from my acquisitions library, to do this, I'm going to import uniform weights. And this just tells it to try uniformly sampling weights to scalarize the problem. You can actually do things if you have one particular blend, for example, you could import, I have another one called fixed weights, and then you can tell it a fixed weight that you think is important for this problem and just have it basically solve that problem over and over. But I'm going to use these uniform weights, and you can add as many acquisition functions to a problem as you'd like. And in my example, the number of acquisition functions determines the batch size when you solve in parallel. So you're if you were to run this in parallel, for each acquisition function, you get one candidate per iteration. So it determines the parallel batch size, but that doesn't totally matter for us. But I'm just going to add, I'm going to do a for loop here, and I'm just going to add 5 acquisition functions to the problem, which would give me a batch size of 5. So that's the add acquisition. And then I have to tell it what acquisition I want to add, and I'm going to use uniform weights. Okay, so I've added 5 acquisition functions to my problem, and now I can just do moop.solve. And I have to tell it how many iterations I want to do. So I'm going to do 10 iterations here. That means that generate 10 batches. So remember, I had a 50-point initial design. I have batch sizes of 5 because I added 5 acquisition functions, and I'm going to solve for 10 iterations. So that's 10 times 5 plus 50. So 100 total simulations would get run in this example. When I run that, it gets some results. What do I do with that? I need to extract my Pareto front, which is basically the solution to the problem. So I have a function for that, my moop.getPF. And this basically gives a NumPy structured array, which is very similar to a dictionary containing all my results. And from here, I can do a couple different things. Let me import matplotlib again. Oh, sorry. I don't want to do that. I want to do from matplotlib import pyplot. This the normal way of doing it. So once I have my matplotlib, I can just, for example, scatter the outputs. So this mypf structured array, it's going to have fields corresponding to the names that I gave each of my things. So it'll have a field for each of the simulation outputs, or sorry, each of the objectives, and it will have a field corresponding to each of the input variables. So for example, I want to scatter my my chi-squared errors against my L2 penalties. And syntax. Does it? Did not pop up. Oh, and I have to do plt.show. There we go. So here's my little trade-off curve, right? If I put all of my weight on sorry, I forgot to add the axis labels here, but this is the fit error and this is the regularization penalty. So I can get I can get a 0 regularization score, right? I can have like basically A, B, and C all equal to 0, and that will give me the least chance of overfitting. But then I have an error of 3 with respect to like matching all my data points. So it doesn't match the data points at all. On the other hand, I can get 0 error on matching my data points, but then I get a very high regularization penalty. So this means there's big risk of overfitting. And then there's a whole lot of solutions in between. And so the last thing I want to do here is just look at all of these different polynomials. So I'm just going to loop over all the points in my solution set, and I'm going to call let's call it from template dot plot poly, and I'm going to plot these A points. So this is my function that I made in the template for plotting the polynomial based on its A, B, and C coordinates, right? So I'm looping over all the points in my solution and plotting all of these polynomials. And then let's look at what that looks like. You can see I have all these families of polynomials, right? And I have some that are really curvy and match my data really well. And then I have some that are very flat and don't match it at all. So that's the solution to this problem. Okay, I am going to stop here. I know I've now run very close to the end of our hour block, but let me just jump back to one of my last slides here. Some things that I didn't cover today because we're short on time. There's a lot of other things you can do. In particular, you can turn on logging and checkpointing. You can use derivatives. You can have different variable types. They don't all have to be continuous. And you can solve in parallel if you have a simulation and you can run multiple simulations in parallel, then you can imagine this could increase your budget. So that might be something you want to do. I layer over this libensemble library in order to do that. And yeah, so these are some other topics. We also have another release coming out very soon. I had a summer student who added a really nice built-in plotting library, so we don't have to import matplotlib all the time. But that will be in the next release, hopefully in the next month or so. But you can check us out. We have a submission under review with Journal of Open Source Software. You can find us on GitHub. These are our docs page. We have some tutorials on there. I don't have this particular tutorial yet, which is why I asked Joseph to send it out in advance, but I have lots of other tutorials and you can pip install us. And I also recently added it to CondaForge with the same formula name. So, and if you have questions, feel free to email me or to our group. So I'm gonna go ahead and stop here. And I don't know if I've used up all the time.
You did, but no problem, Tyler. Really good. I really much enjoyed it. Do you mind if you send us the PDF so we can attach it maybe in the community so people can look through it?
PDF of
the presentation.
Oh, yeah, absolutely. I'll send the PDF of the slides. I mean, I don't have any words on here. They're more just pictures for me to point at. So I don't know how useful that is, but I can certainly send it.
Cool. Sounds good. Right. Any more questions to Tyler?
So I don't see any. So I just wanted to give a couple quick shout outs for myself real quick. First of all, if you use this and you find it useful, please drop us a star on GitHub. It really helps out with making sure we can get funding and stuff to keep this project going. Also, I just wanted to say that we have, if you're a undergraduate or master's or PhD student, we have internships at all levels. I think if you're an undergraduate, it is restricted. You must be a US citizen or green card holder. But if you're a graduate student, if we don't have those requirements for graduate students. And we have people working not just on this project, but there's lots of very cool software packages and stuff going on here. So if you fit some of those categories and you think something like that might be an interesting summer opportunity, please check out our careers page and you can find more information on some of those.
Awesome. Tell us also in our community. So if you want to reach out to him via LinkedIn, maybe I'll also drop a link of your LinkedIn profile in the chat.
Thank you.
Give me a second. All right, there are no more questions, guys. We'll close the session. I'll see you in 12 minutes where Hannes is talking about graph neural networks. It's also going to be very interesting. Thank you very much, Tyler. Really much appreciate your presentation. And the presentation style was really, really good. And I'm looking forward to see you in the podcast, hopefully in November, December. Let's see.
Okay, let me know. Thank you.
All right, guys.
And thanks again for having me.
Yeah, absolutely.